Hi guys, this is Dan Bentley from Section D, and I've just put together a bit of review and preparation for the Unit 6, the calculus test that you guys have coming up. I just grabbed 4 questions that some of my students have asked me about over the last couple of weeks, and I'll just highlight them. Some of these may be easy for you, some of them might be a little more challenging, but I'll just step you through a few of these questions and as I put them out there. The first one, we're going to break up a fraction. It's going to lead to completing the square, and then it's going to lead to an arctan. Okay, and then we're going to look at parts, we'll look at work with definite integral, and then we'll look at the last one as a rotational volume. Okay, so the first question, integrate with respect to x this function. Now, you look at that function and you see a quadratic on the bottom. And you also see that it's an x squared, and then on the numerator, we see a 2x. So I wish that the numerator was in fact the derivative of the denominator. We might be able to actually rewrite it like this. If I rewrote it like this, now my numerator is the derivative of my denominator. This would lead to an integral of natural log, right? But we can't just go and change the numerator like that. What if we just said plus this, a plus 5? If I were to add those, it would be a common denominator, so that would stay the same. And then I would indeed have my function at the top. So here I have now 2 integrals. The first one, I'm going to approach, as I was trying to lead to before, if I let the denominator be my quadratic, then if I let that be u, then du dx is 2x minus 2. And then so this is easily integratable, because I have 1 over u du as I do my substitution, and that leads to natural log of the absolute value of u, and there's my absolute value. I back sub. Now here's just an interesting thing. I have the absolute value, but if you take a quick look, that's a quadratic that will in fact be above the x-axis and never actually be negative. So it's not necessary to have the absolute value bars on those. So I can just write it as natural log of that quadratic. Okay, that's only half of it. Now this other part, if I'm looking at it, I'm going to now integrate this. I can pull that 5 out front, that's a constant, and then I have 1 over all of this. Now we've seen some of these before. If we have a quadratic on the bottom, if it factors nicely, excuse me, this doesn't factor nicely. If we can complete the square, and you remember completing the square, so I'm going to add 1, I'm going to take half of that middle term and square it, so in this case it's negative 1 squared, add 1, and then subtract 1. So if I rewrite that now as x minus 1 squared, a binomial squared, plus 4, what I actually have here is I have the arctan of x. Do you remember this? This pops up. So if you have something that's in the form 1 over a squared plus x squared, or x squared plus a squared, that would integrate to a 1 over arctan. Or, excuse me, 1 over a arctan of x over a. So that fits the mold there. So I can do that. I could say this is 1 over 2 arctan of x minus 1 over 2 plus c. I can distribute that 5 in front there and then clean this up a little bit. Okay, so I have my 2 parts, and I got to remember this is actually just one question, so let's write it all back together. So that just took some sort of breaking up, exploring, and looking at it as 2 different integrals to get that answer. Okay, so all right, let's move on. Here we have an integrate by parts. Okay, so this is a kind of multi-part question. So first it's asking you to do something, and then it says hence. Do something else. So we're going to use what we just found in the second part. But let's start with that first part. Let's integrate by parts. So if I let u, in this case, this maybe isn't necessary, but if I let u be u, then du is 1 over 1 du. And then my dv, I let that be sine u du. So my v would be negative cosine u. Okay, so if I remember my integration by parts formula, is uv equals uv minus v du. Okay, so now I'm going to write that out. So it's going to be u sine u. Okay, so u sine u du is negative u cosine u minus the integral of negative cosine u du. Yep, okay, so du, and then I'll tidy that up, so that integral. So see how that integral of negative cosine u is negative sine u, but because it's a minus, it's plus sine u. So there we have, I've kind of done the first part. Now, because it says hence, I'm keeping my eye on that, and I know that I'm going to be using that in my next question, next part. So let's start with this next part. Okay, so if I let u, they ask us to let u squared be 2x. So that means u is root of 2x. So du dx, so I'm just going to take the integral of that. The integral of square root of 2x. Okay, is 1/2 2x, and it's a little bit of a chain rule happening there. Okay, those that 1/2 and the 2 cancel, and let's see what I'm left with here. Okay, so 1 over, and if you recall, so u is root 2x, so I can replace that with a u. And okay, let's see, if I want to get dx by itself, I've got that u du equals dx. Okay, so I'm going to sub that in. So I'm looking at the integral of sine of 2x dx. And so if I use my u substitution here, this is going to be sine u. And then for my dx, I'm putting in u du. Okay, and now I'm just going to keep working this through. And because I have what I'm using there in purple, all I have to do is I have kind of done this step already here. So all I have to do is fill in what I had subbed in for u. So you can see how that led to the next question. Okay, great. Let's move on. Okay, so this is a definite integral. When you get questions like this that don't actually give you what g at x or f at x is, they just talk about it but have not defined the function as such. Sometimes they look a bit scary, but usually they're actually easier because you just have to really plug in for functions or for derivatives or for integrals. So let's see, let's write this out. So if I want to break this up into two integrals, the integral from 2 to 3, this is a definite integral, of g prime at x dx, well, so that's just the derivative of g, right? So what is the integral of the derivative? Well, it's just actually the function. So the function g at x from value from 3 to 2, plus, now the other part of my integral here is just the integral of negative 1 dx, which is just negative x. Okay, so now I fill this in. Remember, I plug in my g at 3 minus my g at 2, and then I plug in for negative x here, negative 3 minus negative 2. And, oh, they actually gave me what g at 3 is, and they gave me what g at 2 is. See how these actually end up being quite easy? And that's 0. Oh, sorry. So then 5 minus 4 minus 1 is 0. Okay? So I kind of like those questions. They look a little challenging, but they generally end up being quite straightforward. Okay, so the last question is a rotational volume. I've been getting some questions from students on this. Oftentimes you're given a graph, but if you're not, it helps to draw the graph. Hopefully the function's something quite straightforward, like what we have here. So if I want to graph the root of x minus 4, there's my green graph. I want to graph my y equals 1, there's my brownish graph. And then it also says up to x equals 8, so there's the pink graph. So it's a good idea to get an idea, to get a mind's eye of what you're actually rotating. That always helps me. So my shaded region here is what I need to rotate around the x-axis. Okay, so that's going to be rotated around the x-axis. Yeah, there's my y equals 1. But first off, I have to find this point of intersection. Okay, because remember, I'm going to integrate from, I need my two x values. I'm not actually integrating from 4 to 8 here. That would be a common mistake on this question. I need to find that point of intersection. That's done quite quickly. I just set the functions equal to each other and find that x equals 5. In fact, so it'll be 5 and 5, 1 is the ordered pair. But what I'm interested in is the x value. So to find volume, remember it's pi, the integral from 5 to 8 of my top function squared. Okay, that's like a radius squared of my top function minus my bottom function, which in this case is just y equals 1. And that's because we're doing this in rotating this around the x-axis. It could be rotated around the y-axis, remember. So there's a lot of questions like that where you need to get everything in terms of y, and then you look about the function that's furthest away to subtract the one that's closest. So actually the math on this isn't too bad. Once I square out that function, my square root nicely goes away, and I can tidy this up, and I just have x minus 5, and then a quick integral here, x squared over 2 minus 5x from 8 to 5. Plugging those values in, don't forget that pi out front. I often forget about that pi when I'm doing the volume. Working this through, some fraction work here, should give you 9 pi by 2. So my volume is 9 pi by 2, and that's a volume, so it's units cubed. Okay, so there's a rotational volume. Again, draw the picture, look at your points of intersection, and take your top function, or your function that's furthest away from your axis of rotation, subtract your bottom function, and don't forget that each one of those is squared, and don't forget to multiply the pi in after you've done the integral. Okay, well, I think I talked long enough. Those were 4 questions that I've been asked about recently. So I hope that your studying is going well and you're enjoying this unit on calculus, and hopefully the test will be a successful experience for you. Okay, bye for now.